Welcome back to another explainer. Today, we're zooming way in. If you're an embedded engineer or a low-level systems programmer, this one's for you. We're going to completely demystify the exact mechanism that takes your abstract C code and forces it into a concrete, physical binary on actual hardware memory. Yep, we're talking about GNU LD linker scripts. So let's start with a really fundamental question. Where does software actually physically live? When you write a function in C, right, it's just an abstraction on your screen. But a CPU, it doesn't understand abstractions. It only responds to electrical states at exact microscopic physical addresses on a piece of silicon. And the absolute boundary where your software stops being an idea and becomes a physical reality, that is entirely governed by the linker script. Here's our architectural blueprint for today. We'll start with how code meets bare metal, then look at merging object files, the actual anatomy of a linker script, the critical difference between virtual and load addresses, how symbols trigger startup sequences, and finally, some advanced control and debugging techniques. All right, part 1, code meets bare metal. Let's look at how we map that code to physical hardware. Now, before we even write a script, we kind of need to know why we need a map in the first place, right? If you look at the standard compilation pipeline, there's a really clear division of labor. Steps 1 and 2, that's all compiler. It takes your C code and turns it into object files. But here's the kicker. The compiler has absolutely zero clue where these files are actually going to live on the hardware. It just hands out these floating relative addresses. It's not until step 3, the linker, that things get real. The linker's entire job is to take those abstract object files and firmly bolt them down to the physical hardware memory in step 4. And in a typical embedded system, that physical memory is usually split into two very distinct worlds. On one side, you've got your non-volatile flash memory. This holds on to your data even when you yank the power. It's your execution space where your raw code, the .text section, actually lives. Then on the other side, you've got SRAM. This is your volatile RAM, the read and write space where your initialized variables in the .data section and your uninitialized ones in .bss hang out. Okay, moving on to section 2, merging the object files. Think of this as the traffic controller of embedded systems. So remember how your compiler spits out dozens, maybe even hundreds of object files? Well, they all show up at the linking stage totally blind to each other. The linker is the tool that has to merge all these inputs into a single executable. But it can't just guess. It needs a definitive rulebook to route all this incoming traffic, and that rulebook is your linker script. Without it, the linker has literally no idea if a block of code belongs in Flash or if a variable needs to be dropped into SRAM. Every single one of those object files carries a standard payload of sections that we have to wrangle. You've got the .text section, which is your executable machine instructions. You've got .data for global and static variables that actually start with a specific value. Then there's .bss for variables that just initialize to 0, and .row data for your read-only data, like constant strings. The linker script has to find a precise physical home for every single one of these. Which brings us to section 3, the anatomy of a linker script and exactly how it structures the final binary. So let's look at the actual syntax. The absolute bedrock of any linker script is the memory command. I mean, before you can place even a single byte of code, you have to define the physical boundaries of your universe. The memory block tells the linker the location, the permissions, and the sizes of all the available memory on your target chip. It's a hard physical constraint, ensuring your code doesn't accidentally overflow the actual silicon. Let's check out the precise syntax here. We're defining a region and calling it Flash. Inside those parentheses, the RX explicitly tells the linker this block has read and execute permissions. Then we lock in its exact physical starting address, the origin at hex 0800000, and its length as 512 kilobytes. You are literally sketching out the physical chip right there in plain text. Once your physical memory map is locked in, we bring in the sections command. If the memory command builds the parking lots, the sections command is the traffic cop dictating exactly which incoming object files get to park in which specific lots. Breaking down the syntax inside that sections block, it's actually pretty elegant. See that asterisk? That's a wildcard. This specific line tells the linker, hey, go scoop up every single .text section from all of our input object files, smash them together into one giant output.txt section, and then drop that entire block straight into the Flash memory region we just defined. It's incredibly powerful. let's roll into section 4, virtual versus load addresses. This is honestly the climax of embedded initialization. This is where memory addresses take on a dual meaning, and it is absolutely crucial to wrap your head around this. First up is VMA, the virtual memory address. Now, don't let the word virtual fool you. In bare metal systems, we're not talking about virtual machines. VMA just means the runtime reality. It's the exact physical memory address where the CPU expects to find those instructions and variables while the device is actively powered on and running. You have to contrast that VMA with the LMA, the load memory address. The LMA is where your data rests when the power is entirely switched off. So why does this matter? Well, think about a global variable that starts with the value 5. When the device is off, that 5 has to be safely stored in non-volatile flash memory. That is its LMA. But to actually change that variable while the code is running, it needs to live in volatile RAM. So its runtime execution address, the VMA, is in RAM. If you visualize the boot sequence right here, it makes total sense. Your .text section, the code, is stored in flash and executes directly from flash, so its LMA and VMA are exactly the same. But look at the .data section. It's permanently flashed to ROM, so its LMA is flash, but its VMA is RAM. What that means is, in the very first milliseconds of boot up, your initialization code physically has to copy that .data section from flash over to RAM before your main function can even think about running. That takes us to section 5, symbols and startup sequences, or basically breathing life into the hardware. So if your startup script has to physically copy memory from flash to RAM just to initialize variables, how does it actually know where those memory boundaries are? The secret is linker-generated symbols. Since the linker is the one assigning all the final addresses, it generates these critical symbols, like _SData and _EData, and injects them straight into the binary. Think of them as precise GPS coordinates. The bare metal reset handler uses these start and end markers to run a byte loop, copying the flash memory into RAM and effectively waking the hardware up. And you get to define those GPS coordinates right inside the linker script. See that dot symbol? That's a super important special variable called the location counter. As the linker goes through and sequentially places sections into memory, that dot tracks the current address. By using the provide command, your script dynamically grabs that exact memory address at that precise moment in the layout and assigns it to a symbol, like _E text. Finally, let's jump to section 6, advanced control and debugging. Let's talk about handling some common disasters. Because look, when you're dealing directly with bare metal hardware, errors aren't just bugs, they're catastrophic. Miscalculate a length in your memory block? Boom, section overflow. Forget to align a memory address to a 4-byte boundary? You will trigger a hardware alignment fault that instantly bricks the entire startup sequence. Trust me, absolutely nothing ruins a Friday afternoon faster than a silent, unforgiving hardware crash caused by one single misplaced linker constraint. But it's not all doom and gloom. Linker scripts also unlock some incredibly advanced capabilities. Take the overlay command. In embedded systems, high-speed RAM is super expensive and really limited. Overlays actually let you map multiple distinct code sections to the exact same VMA runtime address. So an overlay manager can dynamically swap those sections in and out from slow flash into fast RAM on the fly, depending on what the program needs right then. It's just a brilliant way to overcome hardware limitations using ultra-low-level linker control. And that brings us to the end. As you've seen, linker scripts are the exact point where software directly meets hardware memory architecture. Without them, your C code is literally just a collection of abstract ideas floating in the void. Next time your firmware successfully boots up, definitely take a second to appreciate this massive, silent translation layer doing the heavy lifting. But it does leave us with a pretty big question. If the linker gives you the ultimate power to map your code directly to physical hardware, how much of your system's performance are you leaving on the table by just blindly trusting the default compiler scripts instead of writing your own? Something to think about. Catch you on the next one.